right, welcome back to some more Solidity smart contract vulnerabilities. We're going to be looking at unexpected ether in this one. This one was a pretty interesting one, I definitely thought. So just to give you guys some context here, we'll start off here. I'm not going to read everything word for word, but I'll read this part. So typically when ether is sent to a contract, it must execute either the fallback function or another function described in the contract. There are two exceptions to this. Whether ether can exist in a contract without having executed any code. Contracts which rely on code execution for every ether sent to the contract can be vulnerable to attacks where ETH is forcibly sent to a contract. So basically, like, sometimes people rely on exact values of ether in their contract, and they think that they can just provide some checks to make sure that, when they check the balance, that it's going to be equal to that. But there's so many ways that you can add ether to a contract forcibly, and we'll get to that in a second. But basically, if you code your smart contracts in that way, then you're opening them up for attack, because you can't guarantee that the amount of ether in your contract is necessarily what you expect it to be. And so here they're talking about that basically, right? Invariant checking, right? You check for invariance, right? Normally this is a good technique. You want to check for invariance, right? They're saying typically good design. But an example of an invariant is a total supply of a fixed issuance ERC20 token, right? So as no function should modify this invariant, one could add a check to the transfer function that ensures the total supply remains unmodified and it's working as expected. It says there's one apparent invariant in particular that may tempt developers to use, can in fact be manipulated regardless of any rules they put in place, right? This is what I was basically hinting at before, right? And that is this dot balance, okay? You can't guarantee, like I was saying, the amount of ether in your contract, and here's the reason why. So you can utilize the self-destruct built-in Solidity function, right? So basically what it does is it self-destructs the contract, and it will send all the ether in that contract to whatever contract that you have specified for it to do so. So if an attacker were to create their own contract, right, and say you're implementing this dot balance, and you think you're putting checks in place to ensure to work with this dot balance, right? Now, as an attacker, if I create my own contract and I deposit ether into my contract, and then I set the address for self-destruct to the address of the vulnerable contract, right? What I can do is self-destruct my contract, and all of that ether there will be sent to the other contract, the vulnerable contract, and then that could cause some unintended behavior, basically. So the other way to do this, there is another way as well they're mentioning. I think the simplest way is to use self-destruct. Let's see. So apparently there's like a good blog post on this that has further information. Yeah, present ether is the other way to do this. So, and this was something interesting about Solidity and Ethereum address that I did not know, and it's that contract addresses are deterministic. And they're deterministic in the fact that they're actually calculated from a number of things. For example, the SHA-3, the nonce, all this stuff here that you see. And so it is actually possible for someone to calculate what a contract address will be before it's even created. And so you can send ether to that address before the contract gets created to have those checks in place, right? So once the very moment that contract gets created, it will have a non-zero balance, which again could cause some unintended things to happen, right? Now let's look at an actual example of a vulnerable contract. What would it look like, right? Here's a very simple case. We have an Ether game here. And we have payouts at 3 Ether. Let's see, payout milestone 1, 2, 5. Milestone 2 is 3. And the final milestone is 10 Ether. And your final reward is 5 Ether, right? So we got some payouts and milestones and things like that, right? We have a mapping here from address to uint, redeemable Ether, okay? So first users will pay 0.5 Ether in that specific milestones, credit their accounts. So this play function here, I'm going to require that they send 5 Ether to play. And then the current balance, we're setting it to this dot balance plus message.value. Now here is actually where the vulnerability comes into place, right? And it comes into play, right? Because we were mentioning earlier how we don't want to use this dot balance, but because we can't ensure the value of that is what we necessarily think it is. So we're building out the current balance by using this, which is inherently insecure, right? So ensure no players after the game is finished. So require current.balance less than or equal to final milestone. And then if at a milestone, credit the player's account. So here's the other issue, right? We are crediting these accounts at specific milestones, but we're checking that it's exactly that value, right? So here, right, you won't get your milestone 1 reward until your current balance is exactly the value of payout milestone 1. Now, if we recall, we were using this dot balance, which we cannot ensure the value of this. So if an attacker sent, self-destruct, forcibly sent, and, even like 0.1 of an Ether, it will throw off this exact value because we're only getting in 0.5 increments, right? We'll never be able to reach this exact value. So we'll never be able to no one will ever be able to get paid out, right? And so that's pretty much some of the vulnerabilities and like how they come into play. Same thing with these other milestones here. We're checking for the exact values, right? And then sending the redeemable, we're incrementing it by the milestone reward, right? And then we have the claim reward function here. And it's going to require that this balance, which we don't know the value of, is equal to final milestone. So here they kind of explain a lot of what I was explaining earlier, comes from a poor use of this dot balance. And, you could exploit it with a self-destruct or pre-sent Ether as well. If you send that 0.4, it prevents all the if conditions on lines 18, 21, 24 from being true. Like I was saying, it can never be true because the exact value, it'll never be that exact value. And then, they're talking about even a worst case scenario, right? Is that if an attacker forcibly sends 10 Ether, or an equivalent amount of Ether that pushes the contract's balance above the final milestone, it will lock all rewards in the contract forever, and that's because of this require here. So because it's greater than the final milestone, this dot balance will never equal can never equal the final milestone, right? Because there's no way to take the Ether out. You're just putting it in, other than the payouts, right? But if it was above the value, then you can never actually trigger any of the rewards, so they'll be locked in the contract essentially forever. Because it's greater than the final. And then actually preventing this is a very simple fix, really. You just don't want to use this dot balance. So in this case, they created a new variable called deposited way, and they are constantly they're operating off of that, right? So they're using that to build out the current balance variable they're checking against. And here they're checking against that in the final milestone. Because And then you can ensure that, hey, it's just what is deposited, not the contract balance, which is manipulatable, this dot balance, right? So pretty simple here. That's all you would need to do to really fix this. So yeah, pretty interesting one, I thought, most certainly. And yeah, let me know what you guys think of this series so far. It's definitely been very educational for me, and definitely stay tuned. You know, we're going to kind of go through, get the broad overview, get the big picture of this first, and then we're going to start getting more hands-on with this stuff and actually creating POCs and things like that, which I think will be super interesting. So yeah, definitely subscribe to the channel if you haven't already. Hit the like button as well to help get the message out there, and I will see you guys over in some of these videos on screen if you want to, if you're eager to look at some of the other Ethereum smart contract vulnerabilities that we covered in previous videos. Put that on screen now, and I'll see you guys right over there. Thanks for watching.